Hold a neutron in your hand. You can't, but imagine it for a second. And here is the first fact you need to sit with. It has no electric charge. None. Zero. It is, by every definition physics gives us, electrically neutral. So why does it act like a tiny bar magnet? Why does it deflect in a magnetic field exactly the way a charged particle would, when the entire rulebook of electromagnetism says it shouldn't? You were probably taught in school that magnetism comes from moving charge. No charge, no magnetism. That's the rule. And the neutron breaks it in plain sight, inside every atom in your body, right now. This isn't a fringe anomaly buried in an obscure paper. This is one of the strangest, most quietly explosive contradictions in 20th century physics, and for years nobody could explain it. Today we're going to find out where that magnetism actually comes from, and I promise you, the answer is stranger than the question. Before we go further, let's be precise about what we're claiming, because precision is the whole game here. In 1933, a German physicist named Otto Stern led an experiment using a technique called molecular beam deflection to measure the magnetic moment of the proton, the neutron's electrically charged sibling inside the nucleus. Stern expected a small number. Instead, he measured a magnetic moment roughly 2.5 times larger than the simplest theory predicted. That result alone would eventually earn him the Nobel Prize in Physics in 1943. But the more unsettling discovery came a few years later, when physicists turned their instruments toward the neutron itself. Luis Alvarez and Felix Bloch, working through the late 1930s and publishing their key result in 1940, used a beam of neutrons passed through magnetized iron to measure the neutron's own magnetic moment directly. And what they found broke the rule entirely. A particle with zero net charge was behaving as though it were a spinning magnet, with a measurable magnetic moment nearly 2/3 the size of the protons and pointing in the opposite direction. Read that again. Opposite direction. A neutral particle, magnetically backwards from its charged partner. That's not a rounding error. That's a message the universe was sending, and it took decades to translate it. Here's where I want you to pause and guess. If you had to bet right now on where a neutral particle's magnetism comes from, what would you say? Some kind of internal charge separation, a hidden asymmetry? Hold that guess, because you're closer to the truth than the physicists of the 1930s and 40s were. And that's not an insult to them, it's a measure of how deep this rabbit hole goes. For nearly 3 decades, the neutron's magnetic moment sat in physics textbooks as an unexplained number. Not a mystery hidden by lack of data. The data was excellent, but a mystery hidden by lack of a model. Physicists have the what, they didn't have the why. The why required physics to do something deeply uncomfortable. Admit that the neutron and proton, which had been treated as fundamental, indivisible building blocks of the atomic nucleus since James Chadwick's discovery of the neutron in 1932, were not fundamental at all. They were made of something smaller. That's a genuinely hard thing for a field to admit about itself. Chadwick's discovery had only just settled, a few years earlier, one of the great open questions of nuclear physics: what was actually inside the nucleus, alongside the proton, accounting for the extra mass of most atoms without adding extra positive charge. The neutron's discovery felt, at the time, like an ending. 2 fundamental particles, proton and neutron, cleanly explaining the entire periodic table. Then along comes a magnetic moment measurement that this tidy 2-particle picture cannot explain, sitting there for a quarter of a century, quietly refusing to resolve. Physics doesn't like unresolved numbers. An unexplained magnetic moment isn't a cosmetic imperfection, it's a signal that the model is incomplete, and incomplete models eventually get replaced, however uncomfortable that replacement is for physicists who build careers on the older picture. That idea came from 2 physicists working independently in 1964, Murray Gell-Mann at Caltech and George Zweig at CERN. Gell-Mann called his proposed particles quarks, borrowing the word from a line in James Joyce's novel Finnegan's Wake. Zweig called his aces. Gell-Mann's name stuck. The proposal was audacious for its time. Protons and neutrons, the supposedly elementary particles that make up the nucleus of every atom in the periodic table, were themselves composite objects, built from smaller particles carrying fractional electric charge, charges of positive 2/3 and negative 1/3. Fractions no one had ever measured directly on a free particle before. It sounded to many physicists at the time almost too strange to be real. Fractional charge? Particles that could never be isolated and observed alone. It read more like mathematical bookkeeping than physical reality. But here's the moment where the story turns, and this is the part I want you to really absorb, because it's the actual answer to the question in the title. A neutron in the quark model is built from 3 quarks. 1 up quark carrying a charge of positive 2/3, and 2 down quarks, each carrying a charge of negative 1/3. Add them together. 2/3 minus 1/3 minus 1/3. That's 0. The neutron's overall charge is 0, exactly as measured, exactly as expected. But it is a 0 built from cancellation, not absence. Inside the neutron there is charge. It's just charge that adds up to nothing on the outside while still churning and spinning on the inside. And that distinction, a net 0 built from internal, moving, unevenly distributed charge, is the crack in the puzzle that lets all the light in. Because magnetism, remember, comes from moving charge. If the neutron's total charge is 0, but it's made of 3 separately charged, separately spinning quarks, then each of those quarks contributes its own tiny magnetic moment, based on its own charge and its own spin. And when you add up 3 moving, spinning, individually charged particles, their magnetic contributions don't have to cancel just because their electric charges do. Magnetism depends not just on how much charge there is, but on how it's arranged and how it moves. 2 down quarks and 1 up quark, each spinning, each dragging its fractional charge in a tiny circular current. The electric charges sum to 0, but the magnetic moments do not. That's not a hand wave. That's the calculation physicists did once they had the Quark model in hand, and it's the calculation that finally explained Alvarez and Bloch's 25-year-old measurement. Notice too what this means for the proton and neutron as a pair, because the comparison is where the explanation really earns its keep. The proton, built from 2 up quarks and 1 down quark, has a large positive magnetic moment consistent with its own net positive charge, unsurprising, on the surface, since it's charged and spinning like any other charged spinning object should be. But the theory doesn't just need to explain the proton, it has to explain both particles from the same underlying rule, using nothing but a swap of which quark type shows up twice instead of once. Explaining one number is fitting a curve. Explaining 2 related numbers in opposite directions from a single unified structural rule is a genuine test, and it's a test the Quark model passed. Let's make this concrete with the actual arithmetic, because vague talk of adding up moments is exactly the kind of unresolved sensationalism this channel refuses to leave hanging. An up quark carries charge positive 2/3, and, treated as a simple spinning point charge, a certain magnetic moment scaled to that charge and its mass. A down quark carries charge negative 1/3, with its own magnetic moment scaled the same way. In a proton, 2 up quarks and 1 down, those individual moments combine, according to how the proton's overall spin is assembled from the spins of its 3 constituents, into a net magnetic moment pointing one direction. In a neutron, 2 down quarks and 1 up, the same kind of combination produces a net moment of comparable size, but flipped in sign relative to the proton. That flip is not an accident of the math. It's a direct, testable consequence of swapping which quark type appears twice and which appears once. When physicists ran this calculation against the numbers Stern, Alvarez, and Bloch had already measured decades earlier, the agreement was close enough to be treated as genuine confirmation rather than coincidence, a retroactive explanation for data that had been sitting unexplained since before most of these physicists were born. Let's slow down on that because it deserves to be slowed down. In the simplest version of this model, physicists call it the constituent quark model. You treat the up and down quarks as if they were simple spinning charges with their own individual magnetic moments. Then you add those moments together according to how the neutron spin is built from the spins of its 3 quarks. Do that arithmetic and you get a predicted neutron magnetic moment startlingly close to the measured one. Not exact, we'll get to why not exact in a moment, but close enough that in the mid-1960s this was treated as one of the great confirming triumphs of the Quark model. A number that had sat unexplained since 1940 suddenly had a mechanism. The neutron's magnetism doesn't come from net charge. It comes from unevenly distributed, individually spinning, internally uncancelled charge. Charge that sums to 0 but never stops moving. Now you might be thinking, mystery solved, roll credits. But real physics is rarely that clean, and this is where the story gets more honest, more interesting, and frankly more human. The simple 3 quark model gets you close, it does not get you exact. And in physics, close is an invitation to keep digging, not a place to stop. Here's the complication. Quarks are not sitting quietly inside a neutron like 3 billiard balls glued together. The force that holds them together, the strong nuclear force carried by particles called gluons, is unlike any other force in nature. Unlike electromagnetism, where the force between charges weakens as they get farther apart, the strong force carried by gluons behaves almost the opposite way. It gets stronger as quarks try to separate, effectively trapping them permanently inside particles like neutrons and protons, a phenomenon physicists call confinement. No free quark has ever been observed in isolation, and the theory says none ever will be. But inside that confinement, gluons are not passive. They are constantly being emitted and absorbed by the quarks, and in the process they can briefly convert into fleeting pairs of quarks and antiquarks. A churning, seething internal environment, sometimes called the sea of virtual quarks, layered on top of the three valence quarks that define the neutron's basic identity. The neutron, in other words, is not three quarks. It's three quarks embedded in a boiling, gluon-mediated storm of momentary particles constantly popping in and out of existence. That storm matters because it also carries charge, and it also moves, and it also contributes to the magnetic moment. This is why the simple model gets close but not exact. It's counting 3 players in a game that actually has an entire crowd of temporary participants on the field. To get the precise number, physicists need the full machinery of quantum chromodynamics, or QCD, the theory that governs how quarks and gluons interact. And QCD, in the regime relevant to particles like neutrons, is one of the most computationally brutal theories in all of physics. So difficult to solve directly that physicists had to invent an entirely new technique just to make progress. Lattice QCD, which simulates the quark-gluon interactions on a discrete 4-dimensional grid of spacetime points, using some of the most powerful supercomputers on Earth. Collaborations of researchers running these lattice calculations over the past 2 decades have progressively closed the gap between prediction and measurement, reproducing the neutron's magnetic moment from first principles, quark by quark, gluon by gluon, without simply assuming the answer. That work is ongoing. It is, right now, in 2026, still an active frontier of computational physics, precision QCD calculations refined year over year as computing power grows. And here's a detail that rarely makes it into the popular retelling of this story, though it should, because it's exactly the kind of resolved, not hand-waved detail this channel insists on. Part of that quark-antiquark sea inside the neutron isn't evenly distributed either. Deep inelastic scattering experiments, firing high-energy electrons or muons at protons and neutrons and measuring how they scatter, a technique pioneered at facilities like the Stanford Linear Accelerator Center in the late 1960s, revealed that the sea of virtual quark-antiquark pairs is asymmetric in its own right. There's more down-antiquark presence than up-antiquark presence in a proton sea, for instance, a finding confirmed by later experiments including measurements at Fermilab in the 1990s. That asymmetry contributes its own small correction to the magnetic moment calculation, on top of the valence quark contribution and the gluon field itself. None of this was visible or even guessable from the simple 3-quark picture alone. It only shows up once you're willing to treat the neutron not as 3 particles, but as an entire internal ecosystem, layered and dynamic, that happens to average out to something we can weigh, measure, and fire through a magnetic field in a laboratory. I want you to sit with how strange that is. The magnetism of a neutral particle, sitting quietly inside every atomic nucleus in your body, in every star, in every planet, requires some of the most advanced supercomputing physics has ever attempted, just to calculate from scratch. This isn't a settled textbook footnote, it's a living research problem. Let's rewind for a second and think about what it took, historically, to even get this far, because the human cost of this discovery is not small. Otto Stern spent years refining molecular beam techniques that were, by the standards of 1930s laboratory equipment, extraordinarily delicate, evaporating beams of atoms through vacuum chambers, deflecting them with carefully calibrated magnetic fields, measuring displacements smaller than the width of a human hair, all without the digital instrumentation we take for granted today. He fled Nazi Germany in 1933, the same year he published the proton result, eventually settling in the United States, where he continued his research until his death in 1969. He never won a second Nobel, but that 1943 prize recognized a discovery that quietly overturned the assumption that protons were simple, structureless magnetic points. Luis Alvarez went on to a career defined by scientific range that's almost hard to believe. After his neutron magnetic moment work in the late 1930s, he contributed to radar research during the Second World War, worked on the Manhattan Project, later won his own Nobel Prize in 1968 for his work on particle detection technology, and even later in his career co-developed the asteroid impact hypothesis for the extinction of the dinosaurs. Felix Bloch, his collaborator on the neutron measurement, would go on to help develop nuclear magnetic resonance, the very physics behind the MRI machines used in hospitals today, sharing the 1952 Nobel Prize in Physics for that work. These weren't isolated specialists chasing an obscure number. They were some of the most consequential physicists of the 20th century, and the neutron's stubborn, unexplained magnetism was one of the threads they pulled on along the way. And Murray Gell-Mann, the physicist who named the quark, he'd go on to win the Nobel Prize in Physics in 1969, largely for the broader framework of particle classification that made the quark model possible, a framework he'd developed by looking for hidden patterns in what seemed, on the surface, like a chaotic zoo of newly discovered particles in the 1950s and 60s. What he and Zweig were really doing when they proposed quarks was refusing to accept "we don't know" as a final answer to a magnetic moment measurement that had been sitting unexplained for a quarter of a century. That refusal is, in a strange way, the emotional core of this whole story. A neutral particle acting like a magnet isn't just a curiosity. It was treated by generation after generation of physicists as a debt the universe owed an explanation for, and they weren't willing to let it go unpaid. Zweig, for his part, had a rougher path than Gell-Mann's. His ACES paper was submitted as a CERN preprint in 1964, but never accepted for publication in a major journal at the time. And for years he received less credit than Gell-Mann for reaching a strikingly similar conclusion independently. It's a reminder that the history of physics isn't only a history of correct ideas. It's also a history of which correct ideas found an audience willing to run with them, and which didn't. Zweig would go on to make significant contributions to neuroscience and hearing research later in his career, a career pivot that itself says something about how physicists of that generation treated their training as a toolkit for problems, not a single locked-in identity. And it's worth naming what confinement, the fact that quarks can never be pulled apart and observed alone, actually caused experimentally before it was understood theoretically. Throughout the late 1960s and into the 1970s, multiple experimental groups searched directly for free quarks, in cosmic ray showers, in matter recovered from deep-sea sediment, in oil droplet experiments modeled after Robert Millikan's classic charge measurement technique, hunting for any object carrying a fractional charge of 1/3 or 2/3 an electron's charge. None were ever found. Every single search came back empty, and each null result was itself a data point supporting an idea that, at the time, sounded almost like it was designed to be unfalsifiable. Particles that are definitely there, defined precisely enough to explain a magnetic moment measured to several decimal places, yet permanently, physically unobservable in isolation. That tension between overwhelming indirect evidence and total absence of direct isolation is, again, exactly where the next video in this series picks up. So where does that leave us today in 2026? The neutron's magnetic moment is now measured to extraordinary precision, one of the most accurately known quantities in all of physics, refined over decades of ever more sensitive experiments. And it's not just a settled curiosity sitting in an appendix, it's become a precision tool. Physicists today use neutrons and their magnetic behavior specifically to search for something even stranger, a tiny asymmetry called the neutron's electric dipole moment, a hypothetical, exquisitely small separation of positive and negative charge inside the neutron that, if it exists at a level current experiments haven't yet detected, would help explain one of the biggest open questions in cosmology: why the universe is made of matter at all, rather than being an even split of matter and antimatter that annihilated into pure light the instant after the Big Bang. Multiple international collaborations using ultra-cold neutron sources at facilities in Europe and North America are racing to measure this effect or rule it out to ever finer precision. And the neutron's magnetic moment, the very quantity we've been unpacking this entire video, is the baseline every one of those experiments has to understand perfectly first. If you don't know exactly how a neutron responds magnetically to a field you've applied, you cannot possibly isolate a far smaller, far subtler electric effect layered on top of it. The old mystery became the calibration tool for the new one. You can't chase the second question without having fully answered the first. The mystery from 1940 didn't just get solved, it got promoted. It became the measuring stick for one of the deepest open questions about why the universe exists in the form it does. Think about the chain of reasoning it took to get here. A measurement in 1940 that shouldn't have made sense under the rules of classical electromagnetism. A proposed subatomic structure in 1964 that sounded, to many working physicists at the time, closer to numerology than physical reality. Decades of scattering experiments confirming that structure piece by piece. Each one adding detail the simple model never predicted. Supercomputer simulations, running today, still refining the 5th and 6th decimal places of a number first measured with 1930s laboratory equipment. And at the far end of that chain, an active hunt using neutrons specifically and their well understood magnetic behavior specifically for the reason matter exists at all, instead of the universe being an even, mutually annihilating split of matter and antimatter. That's not a straight line. It's a relay race spanning nearly a century, handed from one generation of physicists to the next, each one only able to run their leg because the previous generation had done theirs honestly, rigorously, without skipping the hard parts. It's also worth being honest about what current neutron electric dipole moment experiments have actually found so far, because a channel built on resolving curiosity gaps shouldn't leave this one dangling in vague mystery. As of the most recent published results from collaborations running ultra-cold neutron experiments, no electric dipole moment has been detected, only ever tighter upper limits on how large it could possibly be, limits that keep shrinking as detector sensitivity improves. That's not a disappointing result. In physics, a rigorously established absence is still data, and this particular absence has already ruled out entire categories of proposed extensions to the standard model of particle physics that predicted a larger effect. Every experiment that comes back empty at higher precision than the last is quietly closing doors on which versions of physics beyond our current understanding are still allowed to be true. The neutron, in other words, has gone from an unexplained anomaly to one of the most sensitive instruments physics has for testing whether our best theories about the universe are complete. Here's what I think is easy to miss in a story like this, and here's where I'll push back gently on how it's usually told. It's tempting to walk away thinking, Quark solved the neutron's magnetism, end of story. That's the tidy version. The honest version is messier and, I'd argue, more satisfying. The constituent quark model got physicists most of the way there in the 1960s, close enough to feel like victory. But full quantitative agreement required decades more of theoretical development, dealing with that seething cloud of virtual quark-antiquark pairs, the gluon field binding everything together, and finally supercomputer-scale lattice QCD calculations that are still being refined today in real time as this video is being made. If someone tells you the neutron's magnetism was solved in 1964 and left it there, they're skipping the harder, more honest half of the story. The part where an explanation gets progressively more exact instead of arriving all at once fully formed. That gradual tightening, decade after decade, generation of physicist after generation of physicist, is closer to how real scientific understanding actually advances than the clean, single discovery narrative most documentaries prefer to tell you. So let's return to where we started. The neutron has no net electric charge, and yet it behaves unmistakably as a magnet, a fact confirmed experimentally since 1940, embedded in the physics of every atomic nucleus around you, right now as you listen to this. The resolution isn't a violation of the rule that magnetism requires moving charge. It's a deeper reading of that rule. Zero net charge can still be built from charge that is very much present, very much in motion, arranged in a way that doesn't cancel magnetically, even though it cancels electrically. 3 quarks, 1 up, 2 down, each spinning, each dragging fractional charge no one has ever isolated and never will, embedded in a boiling field of gluons and virtual particles so complex it takes some of the most powerful computers on the planet to model precisely. That's not a loophole in physics. That's physics working exactly as it should once you're willing to look one layer deeper than the neutron itself. Now here's a question for you, and I mean this one honestly, not as a rhetorical trick. If quarks carry electric charges of positive 2/3 and negative 1/3, and if no free quark has ever been observed in isolation, not once, not ever, in over 60 years of trying, what does it actually mean to say a particle has a charge that can never be measured on its own? Sit with that for a second before you scroll away, because that question is not a footnote. It's the doorway into confinement, one of the strangest and least intuitive ideas in all of modern physics. And it's exactly where we are headed next, because there's a real, documented, deeply strange reason why physicists are confident quarks exist, despite never once catching one alone. It's not faith, it's not a mathematical convenience nobody bothered to question. It's an entire body of independent, cross-checked evidence. Scattering patterns, particle decay statistics, the magnetic moment story we just walked through together. All pointing the same direction, without a single successful isolation to back it up. That combination, overwhelming indirect proof paired with total direct absence, is rare in science, and it deserves its own full investigation rather than a rushed final paragraph here. Before we get there, I want to be straightforward with you about something, because I think you deserve that more than a polished sign-off. Videos like this one take a genuinely significant amount of research time, tracking down the original 1933 and 1940 papers, cross-checking Nobel Prize records, verifying the current state of lattice QCD precision so we're not repeating outdated numbers from a decade ago. If that kind of evidence-first approach to a story is something you value, a super thanks genuinely helps keep this pace of research sustainable. And I don't say that lightly, it goes directly back into the next investigation. Either way, if this rewired how you think about something as basic as a neutral particle's magnetism, that's really the whole point of this channel, and it's worth saying out loud instead of assuming it's obvious. If you think you already know why an unobservable quark still counts as physically real, put your answer in the comments before the next video posts. I'd genuinely like to see how many people get there independently, because it's a better puzzle than most people expect on first pass. And next time, we're going to sit inside that question properly. Why can physicists be completely confident that quarks exist, measure their charges to remarkable precision, build an entire theory of the strong nuclear force around them, and never, not once, catch a single one alone?